Welcome back to Lesson 4 on Great Challenges. As I anticipated in Lesson 3, today, after talking about the great scenarios of history, in the history of global challenges, today I would like to share with you some aspects that have to do with the scientific method. Don't expect a theoretical lesson, because today, too, I would like to share some basic ideas on how science works. It's rather counterintuitive, actually, but I'm going to give you some examples as well. So let me start once again with a slide that we have already seen. We saw it in Lesson 3, but it is the common thread of my course. Not just the classic algorithm of the engineers, so problem solving, decomposition and quantification, but much more that is integrated and works together with this algorithm: relationships, context and history. And today we're going to focus on method. In other words, we're going to talk about the role of humanities. Once again, I'll try to take on a particular perspective. Let's look at science from the outside and let's ask ourselves a question. Why should we trust science? It sounds like an obvious question. We trust engineers because they are able to give working solutions, effective solutions with a function. But are we sure that this is enough ground to trust science? I will make an historical example. You can read more about it if you want. In the past, think for instance of the 19th century, science had formulated wrong theories, which, for instance, included the existence of elements that we later discovered did not exist at all, the ether or phlogiston. Those theories, even though they were wrong, were built in such a manner that, within a certain degree of approximation, could work. Newtonian mechanics for ballistic missiles and some types of uses works perfectly well. You don't need to correct it with Einstein's special and general relativity. So even a wrong theory or a partial theory can work. You can immediately understand that it's not that obvious to say, I trust science because it works, or I trust engineers because bridges and dams stand. Right? So it's not that easy to give an answer to this question. Let's take the example of a phenomenon that we could define as criticism to science or anti-science, pseudoscience. These are phenomena, these are situations which, unfortunately, I'm afraid you will encounter many times in your life and careers. You will encounter political parties or opinion groups or individuals who have stances which are against science. They might deny scientific evidence on vaccines or climate change, or, and which is even more treacherous, you could meet people with pseudoscientific stances, which means they are falsely scientific. In the United States, for instance, there are some evolutionary theories which are fake. They have a religious origin, like intelligent design. Now, if you read these texts, they mimic science. They present themselves as scientific. They pretend they follow all the rules of science, even though they don't. Now, that's very dangerous pseudoscience because it disguises itself as science. Many fake news are built in this way. If you want to face this phenomenon from a scientific perspective, you have to look at all aspects. Now, see, for instance, how many strengths pseudosciences have, because they feed, unfortunately, of social unsatisfaction. Remember, science is perceived as an institution, and today there's a lot of mistrust towards institution. So be aware that you might be criticized as representatives of a perceived establishment or a perceived group of professionals with a particularly advanced knowledge. Many will be suspicious of economic interests that revolve around science. The lack of education, the lack of scientific culture also contributes to the spreading of fake news. Also, there are some cognitive and social mechanisms which unfortunately work very well online. And also, if you remember, we already mentioned it last time, our mind likes certain ways of thinking. it appreciates some shortcuts, some intuitive, emotional shortcuts, and that's why we don't understand climate change that well. But this is true also for fake news. Fake news are rarely made in a naive way by ignorant people. Very often, unfortunately, they are built by people who know very well how communication techniques work. Fake news are presented and told in a very persuasive manner. Our mind, for instance, loves conspiracies. It loves theological thinking, which means finding hidden agents and intrinsic aims in everything that we see. Fake news thrive on all of this. This is why it is so important to answer the question we asked before. Why should I trust science? And why is pseudoscience so dangerous, and therefore I need to fight against it and limit it as much as possible? Now, this is a very interesting piece of research recently published. This is an experiment carried out with students. These students were presented with different types of statements, scientific ones, pseudoscientific, somewhere in between, wrong statements, etc. The experiment tries and see what the best strategies are to destroy fake news, to defeat fake news and pseudoscientific contents. Now, what is the result? The result is that if you only debunk the topic, if you only do a topic rebuttal, and I'm sure you know all about debunking, it's something that you can read about online, that doesn't work that well. So if you see a questionable opinion, you can debunk it. You can check the facts, the evidence, and deny the fake statement. So you can fight bad information with established facts, numbers, and evidence. This does work, but only to a limited extent. It convinces part of the audience, but not everyone. In fact, it has a very negative effect, which has been observed many times. It has a backfiring effect. Part of your interlocutors, those who have a pseudoscientific approach and an anti-technological approach, will become even more convinced of what they think. This mechanism is called polarization. If you don't communicate well, and if you can't explain well how the scientific method works and why we should trust science within certain boundaries, then you will have this backfiring effect. So the best way, instead, which is a complementary to topic rebuttal, the best way to fight against fake news or pseudoscientific statements is the technique rebuttal. In this case, in this attempt to counter-argue fake news, you don't just say it's fake. In addition to this, you also explain how the fake news are built. You basically reveal the method used by those who deny science and try to trick the audience. You're unveiling the tricks, the mechanisms that trick us. In this way, not only you deconstruct the contents of the fake news, but you've also destroyed the mechanisms of the fake news. In this way, you are giving the antidote to recognize and identify other fake news and therefore develop the ability to analyze them in a critical way. Now, my suggestion when we talk about science and scientific method, whether you're talking about it with a colleague of yours who's studied a different type of science, of course, a chemist has a different background than an engineer or a biologist or a physicist, so it will happen to you in your work as well. If you work in interdisciplinary teams, it will happen to you that you will have to explain how you reason, how you work, how you face a problem. You'll have to explain it to a scientist who has a different background, or you might have to explain scientific method to someone who's not a scientist and who maybe has to fund you and give you money, or a politician who should make a decision on a project, or any other kind of situation where citizens need information from you on what you are doing, on scientific contents. Well, here's my suggestion in these cases, which I believe is very important. Every time you communicate about science and you tell about your job, never forget about the technique rebuttal, always tell about the method you follow, the scientific method. Along with the contents of science, you also have to communicate the process, not just the product, what you've understood, what you've obtained, data or a theory, an hypothesis, a model, etc., a project. Also communicate the process that has gotten you there, the strategy, the mechanisms, how you got there. So process and product. This is the Northern Star that you should follow to communicate science well. Now, this is a book that I recommend. I already mentioned it in a previous lesson. This is a book written by an historian of science, Naomi Oreskes. She works at Harvard in the United States. She is a scientist. She studied geosciences and engineering, not too far from what you do, but then she decided to devote her time to the history of science and sociology of science. She wrote a book many years ago called Merchants of Doubt, a very important book. Now, this was the book that explained the wider audience how merchants of doubt work, those scientists, including scientists, physicists and doctors who in the past spread deceptive theories. It happens in science as well, for instance, on the damages caused by cigarette smoke, or on acid rain, on global warming, and so on and so forth. These scientists also did it because they had economic interests or because of conflicts of interest. Now, she's written another book called Why We Should Trust Scientists. Naomi Oreskes shows very well how and why we should trust scientists for the reason I was trying to explain before. Not because science provides certainties. This is something that we already explored in our previous lesson. Science is an endeavor, and you will notice it in your job, that always has to do with uncertainties, with doubts, and with ignorance as well, with things that you don't know and which cannot be explored. You remember that we talked about forecasts, projections and curves going up, the different trajectories and scenarios. Now, those are curves of probability or risk in other cases. They don't provide any certainty. You cannot really know which trajectory will happen or whether we will be somewhere in between. There's always a certain degree of uncertainty, which means that whenever you are asked to provide certainties, don't take up the challenge. Instead, explain why science is all about uncertainty. A wrong answer to this question would be, we can trust science because it is the only form of knowledge that gives us certainty. It's not true. Science doesn't give certainties. However, science provides knowledge that we can trust. Very reliable knowledge in some cases. Otherwise, we wouldn't board a plane and wouldn't trust many results of technology and of engineering. Another wrong answer, according to Naomi Oreskes, is that we don't trust science because it works. As I mentioned before, even a theory that is then proven wrong can work. I don't trust a theory because it works. It can be deceptive as a principle. So the answer that Naomi Oreskes quite surprisingly gives is the following, and I like it very much. I do agree with her as a philosopher of science. She says that we should trust scientists because they get it wrong sometimes. That seems not to make any sense. We trust science because it makes mistakes. Well, that's exactly the case. This is the unique thing about the scientific method, and if you think about it, it's quite exceptional. And it is true for humanities as well to a certain degree, because there is some rigor, but in experimental sciences and in engineering sciences and technology, this is particularly important. You need to learn from mistakes. So science learns from mistakes. It follows a method where you continuously review the attained results. In light of new evidence, in light of new data, you will do that too. And this is the meaning of experimental science. We use existing evidence, so we use the so-called background knowledge, which is always there in science, of course, because as a great sociologist of science, we are dwarves standing on the shoulders of giants. And the giants are those who came before us. Newton was a dwarf standing on the shoulders of a giant called Galileo, and then Newton became himself a giant on his shoulders. Other scientists stood, and you and we are dwarves standing on the shoulders of the giants of the past. You will become the giants of the future, but mind you, the dwarf is standing on the shoulders of a giant, but it's the dwarf who can see further ahead because it has that element of novelty that introduces scientific progress. So, you start from this background knowledge, but then it is integrated, it is questioned. I believe that this is one of the most beautiful aspects of science. In science, there's no pre-built authority, even if they're called Einstein or Darwin or what have you, or Nobel Prize winners. Everybody can be questioned. Of course, you need new data, new evidence, good arguments, a good idea, and you need to be able to demonstrate your idea and present a new model, an hypothesis, an alternative theory. But there's nothing that is unshakable and unquestionable. This is one of the reasons why when you communicate science, you should never present yourself as an authority telling the truth to someone else. Science is a method, it is a process based on skepticism, on doubt, on continuously questioning your own results and the results obtained by others. It is a collective and transformative analysis, because science is always a social endeavor. It is always a collective effort. Problems are solved as a group. Even when you think of a solitary scientist making a great discovery, Einstein, Darwin, Galileo, if you really read their history, you will always find out that they did get to their result by themselves, but that was due to the contribution of many other scientists, maybe less well-known scientists, who gave them the opportunity to look at their scientific problem from a different angle, from a different perspective. In science, very often, you look at things through the eyes of others, and through the eyes of others, by combining data, then maybe you will get to the new intuition, to the new idea, but it's always a collective endeavor, a social effort. Control is collective as well. The first thing that happens in science is that when you're sure of your result, you have to publish it and share it with others. Before you publish your work, it is checked by your peers, and after you've published something, the experiment is repeated, it's checked, it's controlled. So you see, it is a social effort, it is a collective effort. Forget the legendary idea of a solitary genius. It's never happened in science. Every great discovery has always been the result of the work of many people. So we trust science because many work at it, because it's a social endeavor. If thousands of researchers around the world have reached their conclusions, for instance, that climate change is of human origin, well, I can trust this beyond every reasonable doubt. When the probability that an explanation is right is so high, you don't doubt it anymore. It's beyond every reasonable doubt. You never know. One day some new data may emerge, but right now, with the existing knowledge, beyond every reasonable doubt, we know that something works in a certain way. We consider that as a fact, evidence. You see, it's not that easy to explain how science works. It's a process of continuous self-review. Naomi Oreskes also gives other suggestions. One is very important. She says that science is rarely neutral. Science is not just about data, evidence and statistics. It's also about taking a stance. You will have your ideas, your values. Don't throw them away. Don't erase them. The important thing is that your values don't make your work too subjective and too arbitrary. In many of the great challenges we are talking about, values come into play, ethical values as well. You know, the importance of leaving a stable, livable world for future generations. This is not scientific evidence. It's a value. We want this to happen. It is a moral judgment. So many scientists, and rightly so, are also motivated by this and shouldn't hide it when they communicate it. Another way to say all of this, which I believe is very effective, as Naomi Oreskes says, is that it is important to make a distinction between good and bad skepticism. This could be a learning exercise as well. Try and separate good from bad skepticism. What is bad skepticism? You find it everywhere, online, on social networks. It's everywhere, on TV. This is about being suspicious for the sake of it, questioning consolidated science based on nothing, based on no evidence. It's just opinions, suspicions for the sake of it. And this is often based on the certainties. If you go online, there's plenty of people who believe they know exactly how things are, and therefore they question science and scientific contents. Now, that's bad skepticism, but there's also good skepticism. It is the skepticism that belongs to science. Those who are always wary of their results and they keep on questioning them and asking new questions, gathering new data, new evidence, fine-tuning models with humility. Now, this is good skepticism, which grows knowledge. This is the main distinction. If you hear an objection or a criticism, ask yourselves, is it constructive or not? If I listen to this criticism, is this going to help me know more or know better and know more things, or questioning some true weaknesses? If the answer is yes, then that's good skepticism. If the answer is no, then that's bad skepticism. It means that it's not done in good faith. Now, this is a principle that I recommend you should follow every time once you will start your work. I'll tell you an anecdote which is quite famous, especially in my field, but this is interesting to understand some more details on how the scientific method works. Many of you, once you start working in your field of technology or engineering, once you start designing or planning or working in civil engineering and so on and so forth, you will apply the inductive method. What is induction? Simply put, it is about gathering evidence, and then once you have data and statistics, you can formulate a general rule. It is a way of thinking and inference that is very common, very widespread. It's very intuitive as well. I'm not saying it doesn't work. It does. We all use the inductive method. You know, if I observe someone who I've just met and I look at their behaviors, I can see how they speak, how they interact with others, and after a while, by accumulating data in my brain, I can have a picture of that person, or I can develop an idea about their character. I might pigeonhole them in some categories that I have in my mind. Now, that's the inductive method, starting from observational data and then generalizing. Let's say you buy a box of eggs. If you break one egg and you see it's rotten, then you break a second one and that's rotten too. You break a third one, that's rotten too. You don't need to break all other eggs because it's very likely that they're all going to be rotten. Now, that's induction, and we use this method every single day. This makes us trust the outside world. Now, let's see this story from Bertrand Russell, the inductivist turkey. Now, this is a turkey using the inductive method I've just described. The turkey is very thorough, so he notes down all data day by day. He learns that every day at 9 o'clock in the morning, the farmer will bring him food. He sees that he gets food every day of the week, in all circumstances, regardless of the weather, and so inductively the turkey thinks, well, this is a natural law. The farmer will bring me food forever at 9 o'clock in the morning every morning. Unfortunately, this doesn't happen because on Thanksgiving Day in November, the farmer comes and kills the turkey to then roast it. So this is an exception to an inductive rule. What does this story mean? Well, it means that induction is a way of thinking that is very effective. We use it every day in our life, but it's not infallible, quite the opposite. The consequences don't logically descend from premises. They're plausible, they're likely, but they are not a necessary conclusion. In that box of eggs, for instance, not all other eggs are necessarily rotten. It's very likely because the shelf life is the same, but who knows, maybe one egg hasn't rotten yet. It can happen. So you can trust induction, but only to a certain extent. Once again, the outcome is not certainty, but probability. In this case, it was very likely that the next day the farmer would come with food at 9 o'clock, and instead on that specific day it didn't happen. Starting from this idea, a great philosopher of science of the past, Karl Popper, who you might have heard, he was a great philosopher of the 20th century. Do read his books because he wrote amazing books on politics and society. The Open Society, Its Enemies, for instance. He wrote a wonderful autobiography on his life. Karl Popper is the man who developed a very important idea called falsifiability. I hope that I will be able to explain it. What does he say? Well, he says that induction is a method that doesn't produce certainties. So you might say, well, there is another way of thinking used by physicists, for instance, and sometimes by engineers as well. Deduction. What is deduction? What is the deductive method? It is the opposite. You don't start from evidence to then achieve general conclusions. You do the opposite. You start from a general law or rule that you're reasonably sure about, such as the law of universal gravitation. Whatever you study in your courses are consolidated laws. So you start from a general law, and you just need to understand whether the problem that you are studying falls within the scope of the law that you already know. So you have a set of laws with examples, and once you'll have to solve your problems, you'll have to try and understand whether that engineering problem follows the laws of fluid dynamics or aerodynamics, etc. Physics applied to engineering and the related laws. Now, can be sure? Not really, once again. Why not? Well, because it depends on the scope of validity of these laws. You need to be sure that that law truly applies to your case, and you will never be 100% sure. So, you are sure of a law just because you've used induction before. Let's say that deduction would be perfect because conclusions would logically descend from premises, but once again, we cannot trust the method completely. Popper had a genius idea. He said, well, I have found one way of reasoning, which instead makes us trust science once and for all. But it's reversed. This piece of metal does not conduct electricity. Now, this is an observation. This observation implies that it is false that all metal pieces conduct electricity. Such a statement is not all that much. What have I discovered? Well, I've discovered an exception to a general law. True, but there's a big advantage because the conclusion is the logical consequence of the premise. You can't get it wrong. This is a deductive inference that you can be sure about. If you're sure of your observation, I've seen a black swan, you can be sure of the law that says not all swans are white. Well, fantastic! But what's the point of it? What do I do with the statement, not all swans are white? You can do many things, really. And this is the principle of falsifiability. What is the main idea? The idea is that in science, as Popper says, the important thing is not really expecting to be right or demanding for a theory to be true once and for all. The important thing to do is presenting your theory, your model, your hypothesis, your engineering solution to a problem in such a manner that it can be falsified, that someone can go and check and test your idea. What could happen then? Well, your idea might truly be refuted. Not a big issue. At that point, you'll have to reformulate it, rethink it in a different way, and if it's still refuted and falsified, you'll have to abandon it. However, if your theory works and it resists falsification, that means that your theory is corroborated. It becomes stronger and stronger. Today, for instance, 150 years after Darwin, we know that his theory, variation and selection, hasn't been falsified. It's been confirmed. It's been corrected, expanded, reviewed, but the core of the explanation is still valid. The Einstein's general relativity law, for instance, hasn't been falsified yet. It's been corrected in some mathematical aspects, but it's still there because it's been corroborated. It has resisted falsification. However, who knows? Maybe one day someone will find a mistake in that theory, and the same will happen that Einstein did with Newton. The previous theory is incorporated, expanded and corrected. Newton's theory continues to work really well within a certain range of parameters and variables, but in the infinitely small and infinitely large, it doesn't work anymore. So I need a bigger theory, Einstein's theory, which includes the smaller one and corrects it because it explains some anomalies and rewrites it with a different mathematical approach. This is the beautiful magic of science, but as you can see, it is at the basis of everything that you are working right now on your physics or mathematics books. This is what has yielded and created all the knowledge on which your university career is based and your professional career will base as well. If a theory resists falsification, it is corroborated. But remember that everything is temporary. You can never be 100% once and for all sure of the universal validity of a scientific theory. But this is exactly why I can trust science, and this is why Naomi Oreskes is right when she says, I trust science because it makes mistakes. I trust science because it continuously corrects itself. And this is the result of a continuous social dialogue among scientists. It will happen to you as well. You will produce a theory, a product, a piece of research. You'll have to go to a conference or a scientific congress. You will explain your theory. You'll have 15 minutes time. You'll have to be good, short, convincing, effective. And then the debate will take place. Don't take it personal because you will see others will try and question it and make it difficult for you. They will point at weaknesses. They might say, you haven't convinced me, this might be wrong. And you'll have to be good at defending your ideas. This is what science is all about. Science is an antagonistic exercise. You have to defend your ideas from the attacks of others. That's not bad because there are rules of the game. Fair play rules. By resisting the attacks of others, you can strengthen and corroborate your ideas. So the scientific method, it's about conjectures and refutations. New conjectures, new hypotheses, new attempts, mistakes, and so on and so forth. Theories must be continuously adapted to new empirical data that emerge. This is the scientific method. So, of course, it becomes clear that some ethical aspects are also very important, as Popper said. Popper, for instance, said that for science to work, it takes a code of ethics. You need to be willing to be criticized, in theory by anyone, but let's say mainly by those who have good data. The good skepticism I was mentioned before. It takes transparency. For the scientific method to work, transparency is an essential value. If you have a new idea, if you've made a new discovery, a new therapy or a new solution, well, in a very transparent way, you need to explain how you got there with what data so that someone else can go and check and possibly replicate your experiment. This is normally what is done by your peers through the so-called peer review, which means that your peers Of course, this is a method that only works to a certain extent. It's not perfect, but it's the best one we found so far, a bit like democracy. Well, with peer review, you can strengthen, check, consolidate a theory and exclude the weak ones. I will make an example to let you understand how important transparency is. Let's say that tomorrow morning you read on the newspapers that someone has discovered a new therapy, a new treatment based on stem cells against cancer. You might think, well, that's amazing, that's fantastic. It's a very important scientific result. Where did you publish this? What scientific conference did you present it at? And most importantly, what scientific research protocol have you followed? These are the first three questions you should ask anyone who makes such a statement. It's not a random example because it's something that truly happened in Italy some time ago. Now, if the person says, well, I can't tell you. I can't tell you how I got here. I haven't published this anywhere. It's a secret. I'm the only one who knows. And I am experimentally implementing this method, and it's just me doing it. If this is the answer, you don't need anything else. That's it. That's certainly a fraud. It's certainly something that is not respecting the scientific method. There's no point discussing it further. With no transparency, you cannot trust a scientific or pseudo-scientific statement, as in this case. Now, if you've understood how the scientific method works, and by the way, these are slides that I'm going to give you. Now, let's see how a scientific paper is built and how an experimental procedure works. You'll have to follow it too, at least for your dissertation. Once you'll have to discuss and defend your thesis. So learn from these suggestions and these inputs. So you will start from a question. You always start from a research question. With a background knowledge, you already know certain things, but others escape you, so there's a new research question. You ask yourself this question, you gather data and observation. You then formulate an hypothesis. So you develop a conjecture on the possible causes and mechanisms behind a certain phenomenon. You need to be also good at making a prediction based on your hypothesis. So you might say, okay, I want to study this phenomenon. I would like to understand how bacteria, for instance, defend themselves from viruses. So you formulate an hypothesis. That hypothesis must also lead to a prediction. If my hypothesis is correct, then I should do an experiment and find out this. So you can make a prediction. You then carry out the experiment with the right design, with the right equipment and measurements, minimizing errors, following all the technical protocols that apply to experiments. But that's not all. Because there's a second part. You then have to analyze the experiment, write about the experiment, and explain the achieved results. Results might have confirmed your hypothesis or might have refuted the hypothesis. Sometimes wonderful scientific papers are published where the result is actually negative because an hypothesis has been refuted. It can still be very interesting. Finally, you give your final interpretation of the results. So you basically generalize your results into a theory, you try and understand the impact on other hypotheses and so on. You can then publish your paper. The paper is checked by your peers who make sure that all these steps have been followed. Once the paper is published, it can be replicated by others and hopefully produce similar results. It doesn't always happen. It's quite rare that something is replicated. It has to be a very important result, but it can happen. Someone can replicate the experiment, ask new questions, and then research continues. This is how the scientific method works. If you go to Nature and you look at the guidelines on how to write a scientific paper, you will see that it follows exactly the same method. Introduction, so you have to clarify your research, question and motivation, followed by materials and methods, so you explain everything that you've done in your experiment, results, discussion, and finally a conclusion with a possible interpretation. This is how science is made in every field. In engineering, technological and experimental sciences. This is something that you do all the time. It should be done in humanities as well, in a different way, but something similar happens too in terms of rigor. Think of the work of an historian working with archives, for instance, or the work of a philologist. There is still an element of rigor that is very strong in humanities too. So if you look at this cartoon, this is exactly how you work. You have your result, everybody will try and attack it, break it to pieces, question it, refute it. If you get to the end, your paper is accepted, and then the game starts all over again. It's very hard. The work of a scientist is made of many failures. In order to publish a paper, it can take years. You might have to start all over again. It's a work of perseverance, patience, humility. It's very arduous, but sometimes it can also give you great satisfaction. Let's recap. Fake news feed of many elements. So we need to work all together in order to fight against fake news. In order to fight against fake news, we need to be able to answer a fundamental question. Can we trust science? If the answer is yes, as we believe, we need to explain why we can trust science, because it makes mistakes. And I've tried to explain it. The fundamental element of the scientific method, it can be falsified. And so there can be progress in knowledge. Science, as we said, is a collective endeavor. This code of behavior, the method, the procedure I've described requires a society, a community behind it, and that's why we talk about the scientific community. Engineering also has its reference communities, like any science. And by the way, this is the reason why it is so important, when you talk in front of an audience, to always make a distinction between your opinions, your legitimate interpretations, and the scientific consensus in your reference community. That is very important, because scientific consensus is what's consolidated over time, and that is the aspect that we can trust. And then we also mentioned that science is an antagonistic exercise. There are rules of the game, there are fair play rules, transparency and rigor rules, but it's a continuous challenge of ideas, conjectures, and theories. Once Karl Popper said a very beautiful thing. He said, science is very democratic, and it's a great progress of knowledge and civilization because it is the method we have invented to kill theories and ideas instead of killing each other. In other words, we can kill theories because we guillotine them through our control, but we don't die ourselves. It's an antagonistic game of ideas. It's very free. This is the image I'd like to leave you with of the scientific method. But now I'd like to give you some examples. I'll give you another quotation, which I really like, again from Karl Popper. We said before that in science there's good skepticism and bad skepticism. Now, let me add that you have good ignorance and bad ignorance. And Karl Popper says it very well. True ignorance, he says, bad ignorance is not the absence of knowledge. Because all scientists know that they don't know, all scientists know they are very ignorant. And this is why they are scientists, because they want to challenge the unknown, they want to know new things. True ignorance, bad ignorance, is the refusal to acquire knowledge. Ignorant people, says Popper, are those who are full of certainties, full of dogmas, those who obey in authority, while good ignorance is the ignorance of those who know they don't know, and because they know they don't know, they keep on searching, pushed by curiosity and humility, sometimes pushed by madness as well, he says, and by a certain irresponsible behavior. But what is important that once you develop a new idea, you are willing to have it continuously criticized and checked by others. Let's see some examples now. These are examples I would like to make by using some cases which all illustrate a very particular idea called serendipity in science. What is serendipity? I will give you a definition soon. but first let me make an example. Let's start by saying that serendipity is a phenomenon whereby in science you are looking for something. So you have a research question, as I explained before, you always start from a research question. You might even be obsessed and you've thought about that question for your entire career. You can't get anywhere. You can't give an answer. You can't find a solution. And then all of a sudden you find an answer because of a random observation in a very unexpected way, because of the contribution of a colleague or because of a dialogue with someone in a completely unexpected way. That's the first form of serendipity. There's another even stronger form of serendipity, maybe the most intriguing of all. You have a research question and you are focused on it, you're looking for an answer, and along the way, while you're building your research protocol, your experiment, and so on and so forth, you find something that is completely different. You discover something that you were not looking for. And I can assure you that whenever this happens, what you find and you were not looking for is normally very important, a revolutionary discovery. I'll make some example. The most important discoveries in the world of technology and in engineering as well, in all sciences, have happened in a very serendipitous way. At the end of the lesson, I will try and explain why. Let me start from an example. A serendipitous story, one I like very much. Nagasaki, August 9th, 1945. I'm sure you know what happened. Second atomic bomb. Nearby, there's a 16-year-old boy named Osamu Shimomura. He is a Japanese boy. He has been displaced near to Nagasaki after the Hiroshima bombing, and he's hit by a second bomb. When the bomb explodes, he's very close to the bomb because he's on the hills around the city. He's with friends, other boys and girls. They would always go there to look at the bombings and see the American squads. On that day, they see first some scientific instruments falling to the ground because the Americans had also sent some instruments to then see the effects of the bomb, and then they see this huge bomb dropped from a plane, a huge explosion. They see this blinding light. And soon afterwards, this black radioactive rain begins to fall due to the effects of the radioactive fallout. Of course, he runs back home and he's hit by this radioactive rain. He gets to his grandmother because he was living with his grandparents, and following a Japanese tradition that saved his life, he would mention it in his Nobel Prize speech because he would later win the Nobel Prize. Well, his grandmother cleaned him up with a hot bath and he gave him a good scrub down and possibly took away all the radioactive particles. Shimomura would then die at 90 years old in his bed. Quite an exceptional case. So this is the first element of serendipity, if you will. During the following weeks, universities are also displaced and brought to the countryside. Next to his house, the pharmacy and biochemistry faculties are displaced. He has no interest in biochemistry, but that's the only faculty he can attend. He becomes a biochemist. He's very good. He has a good career and he's sent to Princeton. What does he do in Princeton? There is Osamu Shimomura. Well, he does basic research. What is basic research? And this is a very important definition. If you don't know it, it's good that we clarify it for a minute. Basic research, which exists in engineering as well. It exists in application areas as well. Well, basic research is research that is funded not because you have an application in mind, so you don't really know whether what you are researching will become a product or an application. Basic research is carried out because you want to understand a certain mechanism, animated by curiosity. You want to better understand a phenomenon that you're interested in, a biological, a chemical phenomenon. Osamu Shimomura devotes his career to basic research. He falls in love with jellyfish because he's interested in the proteins which in some fluorescent jellyfish produce this bioluminescence, the ability to produce light through proteins. He studies these proteins. He studies this wonderful fluorescent jellyfish, the Aquaria victoria. He understands that this protein reacts differently if it is associated to different elements. To cut a long story short, he discovered the green fluorescent protein, which today is the most important chemical marker. It's used in biology basically everywhere. It is the marker that allows us to see what happens inside cells. It highlights the signals sent between cells. Shimomura in 2008 wins the Nobel Prize for Chemistry because of this discovery. You can see here some mice with the fluorescence. You see where the marker ends because it's been attached to a specific protein. So you can see where the protein goes. An amazing marker. Now, this is a serendipitous Nobel Prize. Shimomura had no intention whatsoever to discover a cellular marker. He had no idea whatsoever that his research on jellyfish would lead to something so unexpected for completely different applications. So this is a strong serendipity. And, of course, I'm sure you've understood the message. Strong science in strong countries is research and science that, to a good extent, is basic research. The greatest technological applications come from basic research. Science has a strong element of unpredictability. You might think, let's say you have a company or you're a public institution, you might decide that you want to spend money because you want to achieve a certain result. You don't always get it. Sometimes you obtain a different result, and sometimes what happens is very serendipitous and you obtain the desired result through basic research. Serendipity is a word that comes from the mid-16th century when a scholar called Horace Walpole writes a tale from Persia, a very ancient Eastern tale, translated in the mid-16th century in Venice by an Armenian man who'd been exiled to Venice, Cristoforo Armeno. Is the tale of the three princes of Serendip. Serendip is the ancient name of the island of Ceylon, Sri Lanka. A legendary island. In ancient times, it was considered as heaven on earth, with fabulous things happening, and Eden on earth. The tale says that a king sends his three children, three princes around the world so that they can become more mature and gather experience. These three princes are very clever. For instance, they can foresee the existence of objects they've never seen. A camel driver has lost a camel. They've never seen this camel, but thanks to the tracks they've seen on the road, they are able to understand that the camel has a limp, is missing a tooth. They know how much it was carrying, and so on and so forth. But they've never seen the camel, and this is what they do throughout the fairy tale. They're great detectives. Science is very much related with the methods of Sherlock Holmes. Many scientific disciplines are based on clues. They're based on many clues. And then you, as a scientist, you have to find the best explanation. So it's an inference towards the best possible explanation. You have to find the most plausible explanation for all the clues you found, just like Sherlock Holmes does when he solves a crime. Walpole reads this tale and he says, well, this is serendipity. Now, this is a buzzword. You can find it everywhere. If you go online and Google serendipity, you will find dozens of millions of occurrences. You will find restaurants called serendipity, shops called serendipity. There's even a movie called Serendipity. It was made 20 years ago, which, by the way, denies the concept of serendipity. It's not that good. It's a romantic movie. You have these two people who fall in love in New York, and then they decide they will split, but they write their phone numbers on a banknote and on the back of a book. They decide they will leave it up to fate. If they'll find their numbers again, then they're meant to be together. Of course, at the end of the movie, they both find the phone number of each other. But that's not serendipity, really, because the message of the movie is that it was fate. They had to be together. That's not serendipity. Serendipity is true unpredictability. This is where the idea comes from. It then it's been widely used to explain many scientific discoveries. This is a very long list. The penicillin, microwave oven, many technological discoveries. Velcro, for instance. Velcro is a very famous serendipitous discovery. Georges de Mestral, an engineer from Switzerland, was holidaying on the Swiss Alps with his dog. He was walking and he observed some flowers from burdock. Burdock is an alpine flower. It's one of those flowers who have an evolutionary strategy whereby they spread their seeds by sticking to animals' fur through little hooks. Many before him saw exactly the same thing, but they hadn't learned anything from it. But he's an engineer. His mind sees certain structures and forms, and so he decides to take that flower and bring it home and study it and put it under the microscope. So he sees how the mechanism works. There's a hook that gets stuck on loops on the fur, and so he comes up with an idea. He thinks, what about a surface with the microscopic hooks and another surface with microscopic loops? If I stick the two together, they will stick without any glue. You don't need any other element, any glue, for them to stick together. One of those discoveries that very simple and nobody had done it before, just like a zip. A zip is based on the mechanism of levers. Now, in this case, it's just hooks and loops. He patents Velcro, which is short for velours crochet, which is then used in space jumpsuits because astronauts don't need a zip. A Velcro works much better, and then it's been used in many, many other applications. But the list is extremely long. Think of nylon, discovered by chance looking for artificial silk, or Teflon is another material that's been discovered in a very serendipitous way, or neon light, or pacemakers. Your life, engineering, is full of serendipitous discoveries. However, serendipity is not just a collection of stories and episodes. It tells us something that is very deep about how the scientific method works. Let me make some other examples. This is another one. Another very famous example, the discovery of cosmic microwave background radiation. You might study it if you choose a curriculum on physics. Maybe you know what happened. The antenna you see here is a very old and archaic antenna. It's the beginning of the 60s. These were antennas used at the Bell's laboratories near Princeton in the United States. They were used for technical and engineering works on the so-called eco balloons, the satellites of the time, the very first satellites. It's part of the history of engineering. Now, this antenna was no longer used, but the Bell Labs, and rightly so, had always funded basic research. So they allowed two physicists, Arno Penzias and Robert Wilson, to use this antenna for completely different purposes, which had nothing to do with the reason why the antenna had been built in the first place. The two decide to point it at the sky to try and monitor the radio signals coming from the sky. They do it, they start and work on their project. At one point, of course, they identify many different human radio sources, but at one point, the two realize that there's always a background noise, which is always there, a constant background noise, which never varies, regardless of the time of the day and regardless of how the antenna is oriented. They exclude all hypotheses. It can't be nearby New York. At one point, they think it could be an interference due to birds. There are some pigeons nesting nearby, but they eliminate this hypothesis too, and still the background noise continues. It's still there. Now, this could be the end of the story, because many engineers and many physicists, even before them, it was later found out, had already heard that background noise. But they never considered it because they thought it was just a fault of the machine. They do something different. by chance, Princeton was one of the places where they still discussed a theory that had actually been discarded by physicists, namely the theory of the Big Bang. It had been formulated in previous years. You know that Einstein was quite critical of the Big Bang theory, and so it had been discarded, it had been put aside. But at Princeton, some cosmologists still believed in the Big Bang theory, so they suggest Penzias to just make one very simple check. According to the Big Bang model, the microwave background radiation, the echo of the initial Big Bang, a wonderful thing, a sort of echo that can still be heard today in the entire universe, well, that should have certain specific characteristics, be in the microwave range, have a certain type of pattern. So Penzias and Wilson make the observation and everything matches. They do other checks and they formulate an hypothesis. And they state that that background noise is not background noise, it is the cosmic microwave background radiation, the fossil signal of the Big Bang. They were right. You know how the story ended. They won the Nobel Prize a few years later for this extraordinary discovery, which then brings back the Big Bang theory and changes physics in the second half of the 20th century. Now, this is also a serendipitous discovery, which adds a further element. Serendipitous discoveries make us understand how ignorant we are, how little we know, and they show us how sometimes, it's happened many times in astronomy, if you have a new technological tool, new things can be discovered. If I point a new technological tool towards the sky, I have many possibilities of finding something that is completely new. This happened many times. We started with optical astronomy, and this was helpful to find out many things, but then we realized that we were just looking at a tiny fraction of what is in the sky. Radio telescopes emerged, and so radio astronomy started, and we could discover many other new things. Another example are pulsars. It's a beautiful example. Pulsars are discovered by chance by radio astronomists, including a young PhD student, Jocelyn Bell, a very good astronomer, and she hears this pulsating signal at one point. The head of her department, the head of the lab, says, "Don't worry about it, it's just an interference. Don't waste your time." But she insists because she thinks it's odd, so she continues to perceive this pulsating signal. She calls it little green men because it really sounded like pulsating signals from aliens. She formulates an hypothesis. She believes it's a rotating star sending these pulses because of this very fast rotation, and this is how pulsars were discovered, neutron stars that rotate extremely quickly. We didn't even know about their existence. Some models had included them, but that was all. By the way, this discovery also won a Nobel Prize, but the Nobel Prize was given to the head of the lab and not to the PhD student. A sad story. The PhD student is still working today, and she's a fantastic astrophysicist, and she's now become a champion of women's rights and women students and researchers in the field of science. Read about this story because it's very, very interesting and very beautiful. This is also a story of serendipity. This went on actually because now we can do astronomy using gravitational waves. It's another eye, it's another Einsteinian gaze to look at the universe and find, for instance, the echo of extreme events such as the collision of two black holes. Once again, we've realized that we know very little about the universe. I'm sure you've read it somewhere and you'll study it in your physics course. We've recently discovered that we truly know less than 5% of everything that exists in the universe because all the rest is dark matter and dark energy. So, ignorance, not knowing that you don't know, as Karl Popper said, this is good. It's not bad. You can learn something else, another lesson from this story. Is there really a difference between basic research and applied research? Yes and no. Pure or basic research has no application in mind because it stems from curiosity. Applied research is more similar to what you do. It's technical research, looking for solutions to known problems. However, we said that very often basic research can lead to discoveries that have an incredible application value, so that turns into applied research. The opposite can happen as well, exactly as it happened in this case. This was applied research. Refining radio telescopes or developing new antennas, discovering or developing new microscopes, that is technological applied research that can open up new worlds for basic research. So another important thing that you have to keep in mind is that basic research and applied research are always interconnected and intertwined. They are not separate worlds. They feed each other. And so a clever state should fund both basic research and applied research. Unfortunately, Italy, as we know, is a country that funds applied research more than basic research, very, very little. I mean, doesn't really fund research that much in general, but basic research even less so. Other examples of ignorance, we mentioned the evolutionary bush in my previous lesson. I showed you the entire bush, but that was a bit of a trick. Now I can reveal it. All those arrows that I showed are all hypotheses and reconstructions. What we really know is this: only tiny fragments of lines, a fossil here, a fossil there, evidence of a different species. But in the end, you see, it is a puzzle. But then I have other knowledge on climate, on the ecology, on geography. So starting from these fragments, I can formulate this bush by bringing everything together. But we have to keep this in mind. It's only an hypothesis. It is a model. The only truth is that imperfect collection of fragments that I showed before. This is an hypothesis to explain it, but it can be reviewed. In fact, you can see that I've already added another arrow, because in the meantime we've discovered another species, so I have to add some more arrows. Science is continuously evolving, always. If you look at this graph, you can learn something new as well. The previous model, the one that I showed in my previous lesson as well, the linear model of human evolution, was very simple, very straightforward, very intuitive, just a few clear, straightforward things, but it was wrong. Now, this is a much more complicated model. It's much more informative because it contains a lot more information, but there are also many questions. Where does the Homo genus come from? We don't know that. On history books, we read about Lucy in Eastern Africa, but we don't know. Now we have new information, and so that answer has become uncertain. We don't really know. Another question mark. Why are we the only human species left on Earth? Well, we don't know really. I've explained an hypothesis, but we don't know yet. So you see, more questions. This is another characteristic, a wonderful characteristic, I believe, of the scientific method. I don't know any other form of knowledge that has this characteristic. The more you know, the more questions increase. It's odd, isn't it? The more you know, the more you realize you don't know. The more you give answers to questions, the more questions you ask yourself. And this is exactly how science and the scientific method work. That's why it is uncertain. That's why it never produces certainties. A few more comments on serendipity. An interesting question could be the following. I'm sure you've thought about it. If serendipity means unpredictability, how can I formalize it? I cannot foresee unpredictability by definition. Well, yes and no. This is an article published on Nature. The title is Lucky Science, and it talks about serendipity. This amazing researcher is a biotechnologist, so he's an engineer of genetics. He decided to become a sociologist of science. So you see that once again, humanities and technical sciences mix. He won an ERC, a big European research grant, to study serendipity, to create a map, a taxonomy of serendipity, and to try and understand, this is the main point, whether serendipity can be somehow grown, promoted and nurtured. His answer is yes. Well, first of all, he created a taxonomy of serendipity, which is quite interesting. He identifies the serendipity that emerges when research in a certain domain leads to discoveries in another domain, or serendipity can happen where unexpected solutions are found to all problems, or also you can have discoveries that are the result of free investigation. And then there's another type of serendipity which is very nice. It's when you find a solution to a problem that doesn't even exist yet. This is fantastic. You find a solution, but the problem comes later. It's happened several times, in fact. In this work, this scholar has also identified the ecology of serendipity. He's identified the elements, the aspects that promote serendipity. A clever observation, new systems of observation, as it happened with astronomy, mistakes and the tolerance for errors. This is very important in science, and I've come to know that it's also important in engineering. Redundancy, errors, it's important to have some tolerance for flexible parameters. It's very important. A great Italian Nobel Prize who emigrated to the States, Salvador Luria, called this controlled sloppiness. What he says is that you need to allow yourself a little bit of sloppiness. You need to be very rigorous. You need to control the sloppiness, but sometimes you can deviate and tolerate deviations and errors. Also, slow science is important. Serendipity is helped by a slow approach, and it's hindered by the desire to be too fast, publish at all costs, by the anxiety to produce paper after paper. That's not serendipity. If you want to discover something serendipitous, it takes time. Basic research needs more time, and so we need to give it more time. And then serendipity multiplies in interdisciplinary groups. The more different perspectives you have, the more likely it is to make serendipitous discoveries. That's quite intuitive, really, because different looks, different perspectives can give you the chance to see aspects that you might not see because you're too focused on your own point of view. At the end of the day, the conclusion is that serendipity comes from basic science and applied science as well. It is the result of luck, a clever approach and the right context, but it also depends a lot on the degree of ignorance. This is a beautiful quotation. This is an engineer, again, an engineer like yourselves. His name is Vannevar Bush, nothing to do with the Bush family of American presidents. Now, he was the engineer who, under Truman and then later presidents, made American science great. He is the man who, after World War II, transformed the United States into the greatest power in scientific and technological research. Now, China is running after them, but the United States are still the greatest power in science and scientific research. Now, the man who created this superpower had this idea in mind. He said that the most important discoveries, now he's talking about medical progress in particular, but he says that these discoveries often come from remote and unexpected sources. And he also says that this is certain, that this will be true in the future as well. Often, discoveries are made in areas that are not related to the discovery that is made in a very unexpected way. So he had understood that if you want to make the science of a country great, you need to fund basic research, because that creates unexpected, remote and unexpected discoveries. I always show this quotation because serendipity and basic research are not important just because we think so, but because they work. And this is proof that those who've invested in basic research and they created a research policies have been successful. So it's proof that it works. This is another interesting graph published by Eurostat some time ago, and it should actually be applied to the pandemic now and to the Recovery and Resilience Fund. Well, this graph shows a fundamental law. The countries who've recovered best from the previous big economic and financial crisis in 2007, 8 and 9, well, those who've overcome the crisis best are always the countries who've invested the most in scientific and technological research, in particular in basic research. There is a very clear correspondence. Those who've invested less have found it more difficult to overcome the crisis, and it's taken them more time. So now we have to overcome another big crisis. The message is we need to invest in scientific and technological research, in particular in basic research. Let's recap. Again, serendipity means finding what you were not looking for. Serendipity means that rarely scientific discoveries and technological innovation can be planned. There is an element of unpredictability. Basic research and applied research are not separated, they feed each other. Also, serendipity can be nurtured. Of course, not by planning it, but by preparing a fertile soil like you do in farming. Let me close with some intriguing examples of serendipity. The main message is the following, and it was expressed a few years ago by a man you probably don't remember, Secretary of State at the time of George W. Bush, President of the United States during the Gulf War. We don't remember him as a great Secretary of State, I have to say, but he's become famous in science because he inadvertently said something that has great value in science. He was called in front of the chamber in the United States. He had to explain that they'd said that Saddam Hussein had weapons of mass destruction. They were never found. And he was asked, well, these weapons, were they there or not? And did you know or did you not know? And he says the answer that he gave. He said, you know, in the world, there are known knowns. In science, that's background knowledge, things we know that we know. No problem there. But in science, there are also things that we know we do not know, the known unknowns. This is also interesting and important in science. For instance, we know that we do not know all the stars in the universe. We know that we do not know all the planets outside the solar system, which could host life. We know we do not know whether there are other forms of life on other planets. We know that we do not know all the living species on planet Earth. I told you last time we know 2 million, but we think that there are at least 8 million. We know we do not know. But Rumsfeld also said that there are also unknown unknowns, things we do not know, we do not know. These are the most interesting of all. This was his answer on weapons of mass destruction, because he said he didn't know, we did not know. Nobody understood what he meant, but that's not that important. In science it works. In science very often we do not know that we do not know. What does this mean? Well, this means that you can make such a serendipitous and unexpected discovery that you realize you didn't even know certain things. You didn't even have the instruments to know that you didn't know. It sounds very complicated, but let me give you some examples. Things we didn't know. Galaxies, viruses, ecologic networks. We know we don't know them. But when at one point you realize that the dark matter and the dark energy represent more than 90% of the universe, now that is something that we did not know we did not know. Before we developed mathematical models on the functions of the universe, we did not know we didn't know this thing. Now we do. And this is an extraordinary discovery because it will certainly lead to a lot more knowledge. Gene editing is another great biotechnological discovery coming from genetic engineering that we did not know we did not know. Microbiologists were doing a research funded with a few €1,000, and they were studying how bacteria defend themselves from viruses. Basic research in microbiology. They discovered that bacteria have invented about 1 billion years ago, so once again the lessons of evolution, they've invented this molecular scissor. They can take the genetic material of the virus, copy and paste it, and recognize it the next time. It's a sort of immune memory. This discovery was engineered, so we realized that it could be transformed into a technology with general applications. That leads to genetic editing, a copy and paste of the DNA. Now, today, this is a technology with enormous fields of application. The landscape of biotechnology has completely changed in recent years thanks to this discovery. It also won a Nobel Prize for these two great scientists, Jennifer Doudna and Emmanuel Charpentier. And this all started from basic research on microbiology. Nobody would have bet 20,000 euro in it. Now, today, starting from that basic research, we have dozens of listed companies doing gene editing. This is the magic of science, the unpredictability of science, and this is the reason why we need to fund basic research. With this biotechnology, we also have some worries now because in a completely unexpected way, we could, if we wanted to, and hopefully not because it would be crazy for many reasons, but if we could create genetically modified children, do we want to do it or not? It's a great ethical issue. Well, for gene therapy purposes, it would be very important, but where is the limit? This research is so important that a world panel is about to be created, like the IPCC, to govern this biotechnology. So you see, time runs very fast, like rolling stones that cannot be stopped. This biotechnology, this engineered biotechnology applied to gene drive, a technology that allows a genetic sequence to be transferred to the entire progeny, overcoming the rules of Mendel. Well, this is something that already happened a few months ago in the Key Islands in Florida. Some genetically modified mosquitoes were released in the environment. The males, when they mate with females, sterilize the females. And that leads to the extinction of a population of mosquitoes, in this case, of virus-bearing mosquitoes, such as malaria or Zika. It all started from basic research. Now, look at this chart that I have taken from Science. Using genetic engineering and synthetic biology techniques, we can even engineer life to the point that in a lab, we can create an organism with a minimal genome. Starting from a bacteria, like a gut mycoplasma, very simple organisms with a circular genome with about 1,000 genes. One by one, all the sequences that are not necessary can be removed. Only the essential ones are kept. The result is a cell, an organism that only exists in the lab with 473 genes. Even in this case, it's an engineered organism. We have 473 genes, but even in this case, we have no idea of what more than 170 genes do. We know that if we remove these genes, the organism dies, so of course they do something essential, but we don't know what the function is. This is ignorance. We know that we do not know. So, of course, now we're going to dig deep into these genes because we will certainly make extremely important discoveries. There are certainly genetic pathways with a fundamental medical and biological value. This is how science works. The last example I would like to mention is the one I was mentioning in the beginning. Sometimes in science, you find a solution to a problem that doesn't even exist. And I think that this is the most fascinating, mysterious and intriguing example. There are many, but I have chosen a very simple one. Edouard Benedictus is a French biochemist and experimental scientist. At the end of the 19th century, he is working on a problem. He was trying to work on collodion, on protoplastic materials. So it was a material engineering research. At one point, an occasional event happens. He drops a glass flask. It breaks, but it holds the same shape. And he sees that the flask has kept its shape. He's very curious about this. So he observes the flask with the eyes of an engineer. He's curious, faced with an anomalous event, a tolerance to mistake. He understands that this is happening because the collodion has created a film inside the flask. So the glass is broken, but collodion is keeping all the pieces together. That's it. End of the story. But he does something very, very clever. He doesn't throw the flask away. He puts it away and notes down the date. Years pass. He works on many other things. He starts reading on newspapers about accidents happening to the first cars on the cobblestone roads in Paris. A car hitting a tree or two cars colliding. The glass breaks and they harm passengers and drivers. He's particularly impressed by the story of a young girl whose face is damaged by the broken glass. So he goes back to his lab, he takes the flask and he invents safety glass. What he does, he takes two pieces of glass, he puts a collodion film between the two, and in 1909 he patents safety glass. He becomes a billionaire. He stops working as a scientist, he devotes his life to art déco, he becomes a great artist of art déco. The first safety glass is used in planes in World War I, and then in all cars in the world, of course, with different technologies, because collodion becomes yellowish, and engineers later on made improvements. But this is one of those discoveries where the solution comes before the problem. Only later you understand what problem that solution can solve. And this is how science sometimes works. Once again, thank you very much for following lesson number 4. I'd like to close with one of the most beautiful sentences I know, written by George Wall, another Nobel Prize for studies on retina and the mechanisms of vision. And he always told his students at MIT in Boston, he said that one of the most important sources of happiness is finding an unattainable goal. Doesn't make sense, does it? It does, actually, because he says that we all, and you all, have goals in life, in your personal life, in your family life, love, study, career. You will achieve them. You will experience great joy, and I wish you all to achieve all of your goals. But Wald also says, remember, nothing is more beautiful than the pleasure you feel while you are trying to attain a goal and an objective. And this is how science works. It's a goal and objective that is always pushed forward. You achieve something, but then another question arises, and then another question arises, and it is an unattainable goal. And he concludes by saying that science works exactly like this. Thank you very much once again.
Vi saluto e vi ringrazio. A presto.